This video shows you how to use the residue theorem to compute some contour integrals. This is much easier than parameterizing the integral and computing it kind of brute force, but it does require knowing where the poles are and computing the residues. So this first integral here, we've got an obvious pole at right here at z equals 3i. The other side, the z squared plus 4, we can actually factor that. Normally can't factor it over the reals, but we can totally factor it over the complexes. Complex numbers, no problem there. Because that's a sum of squares. That means that we have, in fact, three separate poles. The first pole is z equals minus 2i. The second pole is z equals 2i, and the third is z equals 3i. Okay, to use the residue theorem, we want to know which of these poles gets enclosed by our contour, our circle, because those are going to be the ones that are going to factor into the integral. Okay, so the z equals minus 2i, where's that guy? Minus 2i, that's here. Plus 2i is here, so this is minus 2i and plus 2i. And there's the plus 3i. Now our contour is centered at I of radius 3. 1, 2, 3. So it's a circle that looks like that. And in the absence of other information, assume positively oriented. So it looks like we pick up just those two poles that are above the real axis. The minus 2i pole doesn't play a role in this computation. Okay, so that means that this integral, right off, we don't have to do any further work, we know what that is. That's going to be 2 pi I times the residue at 2i of f plus the residue at 3i of f. Now, in order to compute the residues, we need to do a Laurent series expansion around each of these guys. And for this simple thing here, it's actually not that necessary to do. Because, in fact, you might ask, well, how do I find that residue? The way to do it is actually a partial fractions expansion, and that's kind of obnoxious too. Essentially, all you really need to know is you need to find what the coefficient is going to be on each of these. And if you zoom in, say, a very close contour right around 2i, what will you notice? Well, you'll notice that the e to the z part is analytic there and at 2i, as is the z plus 2i, or 1 over z plus 2i, that's analytic there. That'll be 4i, more or less. And the other one will be the z minus 3i is also analytic there. There's no 1 over z minus 3i is also analytic, no problem there. So really, this is going to be 2 pi I times e to the 2i over 2i plus 2i minus 3i. That's this first residue. And notice I've left out the actual thing because this is going to be the coefficient. This is the coefficient on the Laurent series term that is the 1 over z minus 2i. In pretty much the same way, the other residue is not so hard to work out. And of course, there's a similar gap there. And modulo some simplification, that's the end of the story. So a little bit of a detail there. The residue at 2i of f of z. Well, f of z is some analytic stuff plus some coefficient over z minus 2i plus, in fact, in this case, nothing else. That's the end of the story. And so essentially the point is this is the Laurent series. And so you might ask, well, what is this B1? This B1 is just all of this. Because if you put it in and make it look like z is near 2i, this will be a very good approximation. This will be a good approximation. And that's kind of what the Laurent series does. It works like the Taylor series. Okay, now what this means, among other things, is that you don't have to be quite as careful about contours as you might think. So here's another integral. It's got exactly one pole. And you will notice that that one pole is kind of not very related to the circle that we're trying to integrate on, the contour. The pole is at, the pole is at z equals 1. That's this guy here. Sine of z is analytic completely, so it contributes no poles. And our circle is of radius pi. Radius pi is, I don't know, way out here or something. It doesn't actually matter what the radius is. So long as it's bigger than 1, we'll pick up that one pole, and we'll be left with 2 pi I times the residue of sine of z over z minus 1 at z equals 1. And if you were to go ahead and try to compute the Laurent series, which you could certainly do, you'd find that the coefficient on that, the leading coefficient, would be just sine of 1. Pretty neat. Pretty simple. That would have been sort of a pain to compute that integral otherwise, but the residue theorem makes very short work of it.